Okay, so we're talking about electrons. For main group elements, valence electrons are the electrons in the outermost principal energy level. The reason these are important is because being on the outside, they are the ones that interact with other atoms, and so the number of valence electrons has a big effect on how the atom behaves, its chemical and physical properties. So for the main group elements, the group number that the element is in the periodic table corresponds to the number of valence electrons. So oxygen is in group 6A, it has 6 valence electrons. Electrons in the lower energy levels are called core electrons. So in the hotel analogy, the valence electrons would be the electrons that are staying on the highest floor of the hotel that has anyone staying there. And the core electrons would be all the ones on the floors below. So here's part of the periodic table, first 3 periods. So group 1A, hydrogen, lithium, sodium, these elements have 1 valence electron, and that's why they have some similar properties. Beryllium and magnesium have 2 valence electrons. Let's not do all of these. Nitrogen, group 5A, phosphorus, 5 valence electrons. Fluorine and chlorine, 7 valence electrons. And the noble gases, except for helium, have 8 valence electrons. Helium's special, just like hydrogen's special. It's the little baby brother of the element family and gets away with breaking all the rules. I think it's just an exception to everything. The reason that when Mendeleev set up this table that things lined up like they did is because these elements have the same number of valence electrons. So let's write an electron configuration for phosphorus and identify the valence electrons and the core electrons. Well, we need to know how many electrons does phosphorus have. It's got 15. Phosphorus has 15 electrons. So we'll start putting them in the lowest energy orbitals first. So 1s, and we can put 2 electrons in there. 2s, that can hold 2 electrons. Next is the 2p sublevel, 3 orbitals in there, so we can put 6 electrons in there. So we've got 10. I need to do 5 more electrons. So then we get to 3s, put 2 in there, and then the next sublevel is 3p, and we'll put 3 electrons in there. Electron configuration for phosphorus. So to identify the valence electrons, we're going to look at these principal quantum numbers, 1, 2, and 3, and ask ourselves, well, what's the highest number that's listed there? 3, right? So all of the electrons that are in 3 anything are valence electrons. So the valence electrons are the 3s2 and the 3p3. So those are the valence electrons. Everything else, all the things in lower principal energy levels, those are core electrons. So phosphorus has 5 valence electrons and 10 core electrons. Any questions? Okay, now I'm going to show you how you can figure out the order of filling. Remember the splitting and how the levels got all messed up in terms of energy? I'm going to show you how you can figure that all out from the periodic table. We can divide the periodic table into 4 blocks that represent the 4 different quantum sublevels, S, P, D, and F. The group number for main group elements is equal to the number of valence electrons for that element, and the row number of a main group element equals the highest principal quantum number for that element. So the principal energy level that those valence electrons are in. So here we have a full periodic table and it's color coded. So blue is S, pink is P. That's kind of, never noticed that before. Pink is P. D is yellow and F is green. So how many electrons can fit in an S sublevel? 2, because there's only one S orbital in that sublevel. And look, there's 2 columns in this S block. How many orbitals in a P sublevel? 6 electrons, 3 orbitals, right? 6 electrons. How many columns here? 6. So the D sublevel has how many orbitals? 5. So it can hold 10 electrons. You can count them. I'm not going to do it. There's 10 columns. And then the F block has 7 orbitals, so it can hold 14 electrons. And if you get out your finger and count those, there's 14 columns there. Mendeleev didn't know about quantum mechanics when he set up this periodic table. We did not design quantum mechanics to fit the table. We're just trying to explain what is observed, and they coincide just so beautifully. So when we're looking at these different elements and trying to identify what their electron configurations are, well, let's look at magnesium. Start with something small. So here's magnesium. Magnesium is in the 3rd period, and it's in the 2nd column, group 2. So it ends with 3s2. See, this is the S block, the 3s, 1 and 2. So it's got 2 electrons in there. The core electrons are represented by the boxes up here. So this is 1s, 1 and 2, 2s, 1 and 2, 2p, 1 through 6. Those are all the core electrons for magnesium. And the 3s2 are the valence electrons. So you can find the order of filling by just going through the elements in numerical order. Again, helium's being squirrely and he's over here when really he kind of belongs over there. So there's the 2, let's just draw him in there. That's helium. So 1s2, 2s2, 3s2, 4s2, 5s2, etc. So how do we explain that wonkiness with the splitting of the levels? As we're going across here, this is 3p filling up, and then 4s fills up. And if you look back at the order of filling that was given in the book, the next one is 3d. Well, this is the D sublevel, but it's not 4d. And the way I remember this is I think of it as being sunken. Like it was supposed to be up here, but it sank down a level. So this is really n equals 3, but it's sunk. So it's the period number minus 1. So for the D block elements, it's your period minus 1. And we'll see that for the F blocks, it's the period number minus 2. That's what n is equal to, the principal quantum number. So this is 4s, and then we get to 3d. You fill all those up. Now p is regular again. So this is 4p, 5s. We get to the D block. That's not 5d. It's one less than that. It's 4d. 4d filling up. This is 5p. 6s. This would be 5d because it's sunk. And then, notice this is 57 and that's 72. I don't know how you count, but 72 is not the next number. It's 58, right? What happened to it? Well, it's down here. See the arrow? Now, the one we have on the wall here, because of the limited space, we have it displayed in its full glory. And so over on this one, we've got 56, 57, 58, and they just go nicely in order. So this is 6s, and then this is f, and it's 6 minus 2. So this is the 4f in here. So these guys are 4f, and you get to the end of those, and you pick up here, and so that's 5d. Now there is this weird little glitch here. There's one electron that goes into the 5d before the f starts filling. We're not going to worry about remembering that. So yeah, it's there, but don't worry about it. So 5d going across, 6p, 7s, kind of skip that guy. Now we're down here. This belongs in period 7, but the f is 2 numbers below. So this is 5f. So the 5f fills up, then we're back to the d. D is 1 less than the period that it's in. This is 6d, and this would be 7p. This is an older periodic table. We do have letters for all of those letters and names. Any questions? Does it make some sense? So if you forget how many electrons can be in the p sublevel, all you have to do is count these columns. That's how many. And you count these for d and those for f. So S, P, D, and F. And then remember for D, you know, here we had this stair step coming down. It looks like it should be right there, but it sank. Do you know they say the valley floor is sinking because of the water table sinking? So this looks like the valley. The valley floor is sinking. So it belongs up here. So this is 3. We take this period and we subtract 1. This is 3D. And then these guys have sunk even further. And so those would be the period minus 2. Okay, so let's practice this a little bit. Writing an electron configuration from the periodic table. And I think this is the best method because if you're doing chemistry, you're going to have a periodic table. So it's just with you. You don't have to learn the other method. So let's write the electron configuration for chlorine using this periodic table. So we're going to do the noble gas shorthand one. So if we want chlorine and we're going to do a noble gas configuration, then we just go up 1 row and over to the end to find out what that noble gas is. So I'm going to write the noble gas symbol in brackets. That represents the electron configuration of neon. And then let's look what comes after neon. We come over here, this is period 3, so this is 3s, and we go 1, 2, so 3s2. And then we jump across this chasm here. This is 3p, 1, 2, 3, 4, 5. 3p5. That's the electron configuration for chlorine.
So is it a covalent?
Pardon me?
Is it a covalent electron?
The fans are too loud, I can't hear.
Is it a covalent?
Covalent. Yeah, chlorine is a nonmetal and it forms covalent bonds. It can also be an ion. What if we wanted the full electron configuration? Well, just start at the beginning. There's one S and there's the other, so there's one S2. So let's do this. So we did that. And then we're doing this, and this is 2S2, and this is 2P6. And we come over here, 3S2, and here we're 5 into that one, 3P5. So you can just scroll through the periodic table, counting how many columns there are, remembering the blocks and looking at the period numbers, and it's all there. let's do the electron configuration for bismuth. Here we have a more normal periodic table that's not color-coded for the different sections. Well, bismuth. We got to find it first. It's down here. So there's bismuth. Just for grins, let's do the full thing, just for some practice, okay? So if we're going to do the full electron configuration, we're going to start at the top with helium. And helium is 1 in the S block, and then there's this weirdo helium over there, hydrogen and helium. So let's see if I can fit it on one line. 1s2. Then we're in the second row, S block, 2s2. And we come over here, still in the second row, that's the P block. We went all the way across, 1, 2, 3, 4, 5, 6. 2p, 6. Then we come to the third row, that's 3s2. Skip that big open space, 3p, all the way across is 6. Then we come here, 4s2. And now we get to the D block, and we have to remember that's not 4D, that's 3D. So 3D, all the way across. If you forget how many, you can count. That's 3D, 10. This is the main group again, and so it's regular. This is 4p, all the way across, 4p6. And then over here, 5s2. And again with the P block, the D block, this isn't 5, it's 4. So this is 4D, 10. And then this is 5p, 6. 6s, 2. And then this is where things get really strange, right? So there's that guy right there. We're just, because we're going past him, we're going to skip him. And we're going to come down here to the F block. And that one's full. That F block was in the 6th row. But the principal quantum number for that is going to be 6 minus 2. So that's going to be 4F, 14. And then we're going to pick up here in our D block. The D block is whatever period it's in minus 1. So that's 5D. 5D, 10. I almost made it. And then this is back, main group are just the same as the period number. We had 6p, 1, 2, 3. Kind of off the side there, 6p3. Do you see how I did it? Does anybody have any questions? Yeah.
So I heard the last part where you take the side number and subtract it by 1
Mm-hmm.
to get the...
Yeah, so for the main, this is an S block, and this is the P block, and those are the main group elements. They're the parts that stick up. So for these P, representing P orbitals, the principal quantum number is the same as the group number. So this is 2s, and this is 2p. Down here, this is 5s, and over here is 5p. But the D block in the middle, I think of them as being sunken, because they look like they should, stair steps, like they should be up here, but they're not. So in the D block, you take whatever the period is and you subtract 1. So 4 minus 1, this is 3D, 4D, 5D. And then the Fs are sunk 1 more. And so it's the period minus 2.
And the number on top, how's that determined?
So the exponent is, we're looking at, each of these represents an additional electron being added. And so in this 2s block, there's the first electron in the 2s, and there's the second. So that's 2. And then we come over here, this is 2p, 1, 2p, 2, 3, 4, 5, 6. So you basically just are counting the squares, and that will tell you how many electrons are in that part. So you count, I'm going through 6 here, so that was 2p6. Here I've got 3s, there's 2 of them over here, 3p6. Okay? Once you see it, it's very simple, but you have to ask questions until it makes sense. Okay, let's write electron configurations for each of these elements, and we don't have a periodic table on the screen. So, chlorine. Do you want more practice doing the full thing, or do you want to just do noble gas? Noble gas? Okay, so chlorine, we're going to look up and over what's the noble gas before chlorine. Neon. And then after neon, we go over to sodium. Sodium is the first electron in 3s, and there's 2 over there, so 3s2. And then we come across, and we're in the 3p block, and aluminum, silicon, phosphorus, sulfur, chlorine, that's 5. 3p, 5. So silicon has a fewer electrons than chlorine. So neon is still the previous noble gas. And we go through the 3s2 in the s block over there. And then for silicon, we're again in the 3p block, but it's the second element. So aluminum is 1 and silicon is 2. So this will just be 3p2. You can check yourself by adding up the electrons. The superscripts represent number of electrons. So I've got 2 electrons here and 2 there, that's 4. And then how many electrons does neon have? It's element number 10, it's got 10. So 10 plus 2 plus 2 is 14. Silicon is element 14. That's encouraging. It doesn't prove that I did it right, but it's encouraging. How about strontium? What noble gas is right before strontium? Krypton? So krypton is at the end of period 4. Strontium is in period 5. So after krypton, we're going over to the 5s. 2. There's rubidium and strontium. 5s2. Oxygen's a little one. Let's just do the full thing. So for oxygen, we're going to start with hydrogen and helium. Those represent 1s, 2, the 2 electrons filling the 1s sublevel. And then we go to the second period, and we've got 2s2. And then we jump over, and we're in the p block, and oxygen is the 4th one in. Count the boxes, 1, 2, 3, 4, 2p4. You can add the superscripts, she gives us 8, and oxygen has 8 electrons. Any questions?
Did you do the silicon one again?
Yeah. So for silicon, we're going to look, actually, literally getting turned around. Let's do it on this periodic table, so the people at home can see what we're doing. So there's silicon. If I want to do the noble gas electron configuration, I'm just going to go up to the next row, the row above, and look over here and find out what's the noble gas that's immediately before. So that's neon. So write him in brackets. And then I go, well, what's after neon? I've got these 2 guys. That's 3, that's the S block. There's 2 of them, so that's 3s2. And then we come over here, we're in the second one. This is the 2p block. I'm sorry, 3p block. 3p, and I've got the 1, 2, so it's 3p2.
Okay, I started counting after the staircase. That's why I was like, why is it?
Yeah, you're looking at these big blocks here. And there's 6 columns, 1, 2, 3, 4, 5, 6, because the p subshell can hold 6 electrons. Yeah.
Can you show the we were on the bottom diagonal?
On the diagonal?
Or diagram?
Oh, with listing out all the things and drawing the arrows? I'll show that to you in lab. I'm not going to do it on YouTube. I'm not going to. But I'll show you in class later. So that's really great and everything, but of course there have to be some rule breakers. So we've got this sublevel splitting, and that's due to the interactions of the electrons. There's shielding and then penetration into that shielding. That's what makes the 4s level slightly lower in energy than the 3D, and that's why the 4s fills before the 3D. But the difference in energy there is not very large, and so it's relatively easy to find exceptions among the elements. So the transition elements are the ones that just are often irregular, and so they have some strange behaviors. These are not things that you can just predict from the periodic table. They were determined experimentally, and then we do our best to try to remember what they are. So here are some that your book points out. And I'll just tell you, I want you to know this one and this one. So those are the 2 I want you to remember. The rest of them, we'll talk about them, but that's it. Okay, so chromium. You find chromium on the periodic table. It's the 4th block in this 4th square in 3D. And so this is what we would expect. Argon, 4s2, 3d4. But that's not what it does. So I'm going to draw the electron configuration, the orbital diagram, because that might help us be able to see what's going on here. So we expect that those 6 electrons after argon, let's label these. This is 4s, and this is 3d. That we put 1 electron here, and then 1 in here, and then the next 4 would go 1, 2, 3, 4. That's the pattern, right? But that's not what it does. What it does is it takes this 1 electron over here and puts it in there. Now, what's really nice about that picture? All the electrons are pointing the same way, and they each have their own orbital. Everything is half full. It's like, oh, well, that's kind of cool, right? So this, in the hotel, this is like, there's this coupon special. It's like if you hop on your left leg on the 3rd Tuesday, you can save $5 on a bag of, potatoes. Right? Weird coupons. So there's a lowering of energy when we have either half-filled subshells or completely full subshells. So that's what chromium does. So we go a little further and we'll find copper in that same row. We expect copper to look like that, because you fill the 4s first and then you fill in the 3D. But here we have, this one's full, but this one's like just really lopsided. This is like 9 and it should be 10. So what can happen, because the energy difference is small, this electron moves up here. And now what we have is this subshell completely full, this one exactly half full. That's slightly lower in energy, and so that's the explanation for why copper does that. Okay, so I want you to remember the irregular electron configurations for chromium and copper. I will try to mess with you on an exam with those guys. There's an exam next Thursday, so pretty much count on one of these being on there. The other ones here, molybdenum does a very similar thing to what chromium does, so that kind of makes sense. Ruthenium, I have no idea why it does this. So it should be 5s2 4d6, but this one goes up and it's 4d7. I don't know. That would be, let's see if I can. One, two, three, four, five. Yeah. I don't know why that's good. Got me. But it is. That's what ruthenium does. It doesn't matter if I like it or not. Palladium is also irregular. What palladium does is it takes both of those s electrons and bumps them up. So we get an empty subshell and a completely full subshell. So you don't need to remember those last three or any of the other ones you might come across, but you do need to remember chromium and copper, and just know that there are irregular electron configurations.